So I will wait for 1 minute more, okay? So hello everyone, this is Anjali Negi. So I will introduce myself a little bit. So I am pursuing PhD currently in IIT Kanpur. So this session today I will not play the recording, but I will myself will teach you, and uh, similarly in the same manner of first introducing the problem, then going to some basic, and then solving that particular problem that we have. Also, I have one another, I think, what was her name? Okay, yeah, Gunasili. Yeah, she asked me to teach the difference between the nephroxetic series and the spectroscopic series. So I have that also prepared. If she joins the tutorial today, then I will just discuss it. But let's move into the problem. Okay. So since I am recording the content right now only, so I request all of you to ask your doubt after I am finished. Okay. Okay. So let me share my screen. What is that? So you guys are able to see my screen? Okay. So am I audible, right? Shika?
Yes, ma'am.
Okay, yeah. So I will start now. So this is the problem that we have, that is GATE 2012 chemistry question number 52. This is a linked question that says that we have a 20491 centimeter inverse laser line was used to excite oxygen molecule to obtain the rotational Raman spectrum. The resulting rotational Raman spectrum of oxygen molecule has the first Stokes line at 20479 centimeter inverse. So we are given with only these two information, and then we have to find out. The first question is part 1, that the rotational constant, uh, the B value for the oxygen molecule is. So we have to find out the value of B. So in the second part we are asked to find out the next rotational Stokes line is expected at. So let's move into the basic of this problem. Yes. So yes. So talking about Raman spectroscopy, okay, so usually the rotational, vibrational, and electronic spectroscopy involves the absorption and the emission of light. Okay, but in Raman it involves scattering of light, which we can actually demonstrate simply as our matter. So we can simply demonstrate it as our matter when interacting with the incident light such that the incident light intensity is I0 and the wavelength is lambda. After the interaction, I have transmitted light having my intensity IT, and the lambda value is same with the incident light, that is lambda. Again, I can have another light other than the transmitted light, that is scattered light, correct, which have intensity is, okay, but the lambda value can be different, like it can be same as the incident one, or it can be different from the incident one. So when my lambda value is same as the incident one, it is what we call as Rayleigh scattering, okay. And Rayleigh actually said said that the scattered light intensity, that is is directly proportional to the lambda to the power -4. This lambda is actually the lambda of the incident light, okay, the wavelength of the incident light. Or we can actually just write it as directly proportional to 1 upon lambda to the power 4. The other type of scattering in which the lambda, that is the wavelength of the scattered light, is different than the incident one, is known as the Raman scattering, okay. In Rayleigh scattering, this is the example where you can define why the sky have blue color, okay. Just think about it, okay. Now coming to Raman scattering, what happened in so Compton scattering was earlier we know that it is the X-ray was scattered by electron, and the wavelength of X-ray was changed, okay. So Raman thought that there must be an optical analog of this Compton effect that he called as Raman effect. So basically in Compton effect, what happened was that the X-ray, when interacted with the electron, then the wavelength of that X-ray got changed, okay, by lambda dash. So this was Compton effect. So in Raman effect, which was given in 1928, the date is actually 28th February, that we in India celebrate as the Science Day, okay. So the classical theory for Raman effect is that the electric field which is interacted with the matter is it induce some dipole moment in the molecule. Now this oscillating induced dipole moment is the source of electromagnetic radiation, and it results in scattered light. So the scattering can happen in two ways that I have just taught you previously, that majority of it have the same wavelength with the incident light, okay. So or frequency that we can say, so mu 0, so same as the incident, and hence we call it as the elastic scattering, okay. But in other kind of scattering where my wavelength or my frequency is changed, that is mu 0 dash, we call it as inelastic scattering, and this is what we observe in Raman scattering. So in classical theory, the induced dipole moment strength, the mu induced, can be given as alpha E plus 1 by 2 beta E square plus some higher order terms, okay. So this alpha is simply polarizability constant, and beta is hyperpolarizability constant. So all of these depend upon the nature of the molecule, the structure and the nature of the bond. So E is the electric field strength that was applied on the matter to interact. So coming towards the quantum theory. Now quantum theory of Raman effect says, so this is this one where photon is observed by my matter, say M1 having energy E1, the matter is same, so energy is different now after the interaction of the photon H mu, so it becomes energy E2. So in this kind of interaction that actually happens other than Raman spectroscopy, we see that the energy conservation can be simply written as E1 plus h mu is equal to E2, where my delta E can be given as equal to h mu, correct? But for Raman scattering, where it is a inelastic scattering, so for that what will happen, that photon 1 will be there, which will get not fully absorbed, but we have a emission of the photon 2, which is having energy h mu 2, correct? And this depending upon whether this h mu 2 is equal to h mu 1, it will be Rayleigh scattering, or depending upon whether this h mu 2 is greater or smaller, it will be Raman scattering. Okay, so yes, so here again if we apply the energy conservation, we see that E1 plus h mu 1 is equal to E2 plus h mu 2, where I can simply write, taking h Planck's constant as common here. So we have mu 1 minus mu 2 is equal to E2 minus E1. So if my energy E2 is greater than E1, so remember that this E2 energy is for after the interaction of the photon. Okay, so if my energy after the interaction of the photon gets higher, that is my E2 is greater than E1, simply means that my h mu 1 is greater than h mu 2, correct? And my lambda, that is my wavelength of lambda 1 will be smaller than lambda 2. So this wavelength of scattered light is higher. So lambda 2 is the wavelength of the scattered light. So scattered light wavelength is higher than the incident light. In that case, we say that we get the Stokes line. Okay. In the case where my energy is of my after interaction is lower, okay, such that the wavelength of scattered light is lower than the incident light. Now, since the wavelength is lower than the incident light, the frequency is higher than the incident light, and hence we get anti-Stokes line. Okay. So what is Raman effect? So Raman effect can also be defined by time dependent perturbation theory. So this is, I am quickly going through because I hope you guys know it. So first of all, we have our molecule in our initial state, and then it goes to a virtual or intermediate state, from where it finally goes to the final state. So just demonstrating what I have said, that we have a initial state I, final state F, and a virtual state V. So when I have a virtual state V in the case number 1, so this is say case 1, my photon h mu 1, which is the incident photon energy h mu 1, when my matter interact with it, it gets from initial state to virtual state and then comes back again to the same initial state. So releasing h mu 2 as a scattered light. Here this mu 1 is equal to mu 2, and we say this as a Rayleigh scattering. And the other case where, so in the other case where my incident photon interact from taking from the initial state to the virtual state, and then coming from the virtual to the final state, such that my h mu 2 is released. So this says that my mu 2 is lower than mu 1, and my wavelength of mu 2 is greater than lambda 1, that is the incident one. So my scattered wavelength is greater than the incident one, and hence this is the Stokes line. Again, for the anti-Stokes line, what we have that it goes from, the excitation is from the some final state to the virtual state, and then it gets back to the initial state. So here the point to be noted that the incident photon having a frequency mu 2 is greater than the frequency mu 1. Okay. Yes, and the wavelength will be, the wavelength of my scattered photon is smaller than the wavelength of my incident photon. So this is the anti-Stokes line. So in quantum model, so there are Raman, when we say Raman spectroscopy, so there is a vibrational Raman spectroscopy and rotational Raman spectroscopy. In our problem, we are given with rotational Raman spectroscopy. But in the case of vibrational Raman spectroscopy, so in that particular case, the intensity of Stokes line is always very greater than the intensity of the anti-Stokes line. Why? Because uh, if you say the vibrational Raman spectroscopy, then the vibrational energy level are having a very bigger gaps in the level okay. In the state of vibrational quantum number 1 to 2 to 3 to 4, the gap increases, and hence the population density is much higher in the ground state. And since we know that in a quantum model, the intensity is dependent on the population of initial state given by Boltzmann distribution. And if we do the ratio, take the ratio of intensity of Stokes versus intensity of anti-Stokes, so this will be equal to, so if you remember, I have told you that the intensity of scattered light was inversely proportional to lambda to the power minus 4, and hence since it's lambda to the power minus 4, we will have frequency to the power 4, correct? And I can just write it simply like this, and this is the Boltzmann, this is coming from the Boltzmann distribution. And since you see that the ratio depends upon temperature T, and we know the vibration energy levels having higher gaps makes this temperature also take place role, and the population is much higher in the ground state in comparison to other. And that's why we know where it is, yeah, from this particular diagram, that the excitation will having intensity is much higher in the intensity of Stokes line in comparison to the intensity of anti-Stokes line, which is the excitation from some higher energy state than the ground state. Okay, so this is for the vibrational Raman spectra. Now coming to the rotational Raman spectroscopy. So always remember that generally in rotational spectroscopy we have a selection rule of delta J is equal to plus minus 1. But in rotational Raman spectroscopy we have a selection rule of delta J is equal to plus minus 2. So now just these are my rotational energy levels, some initial and some final. Okay, and this is my virtual state. So the excitation takes place from initial to the virtual, and then coming back from virtual to the final, and such that the delta E, that is the energy gap, is this delta E. So the energy for rigid rotor model, that is my EJ is equal to BHC capital J whole bracket J plus 1 joules, and this delta J is equal to plus minus 2. So if I calculate delta E here, so just simply put delta E as, so it will be the difference between EJ minus EJ plus 2, correct? And then just put the formula as it is and solve it. You will get delta E is equal to 2BHC whole bracket 2J plus 3. Yeah. So if I convert this energy difference into the wave number, okay, so now the spectroscopy, the spectrum that we see is, we will convert this delta E into the wave number. So simply what I just have to do, I have to divide it from HC. Okay, so this delta E is equal to HC wave number, and this wave number is equal to delta E upon HC. So dividing this equation by HC, so I will get wave number is equal to 2B whole bracket 2J plus 3 centimeter inverse, where I can put my J is equal to 0, 1, 2, any number. Okay. Now can I put the expression as, so my wave number is equal to the wave number of excitation light or excitation, that is the incident light. So the wave number of the incident light plus minus the delta E, or the plus minus the wave number of the delta E, which is converted to the wave number. So we solved it and we got 2b 2j plus 3. Okay, so this will be plus minus. So in the case of plus, okay, so in the case of plus we get anti-Stokes line, in the case of minus we get Stokes line. Okay, so basically if you draw, so these are the rotational energy level. So J equal to 0, 1, 2, 3, 4, and we are doing rotational Raman spectra here. So the selection rule is delta J is equal to plus minus 2. So from J is equal to 0, we will go to excitation will be up to J is equal to 2. If I am at J is equal to 1, then the excitation will be J is equal to 3. And similarly, the emission will be in the same manner, that is from J3 we will have up to J equal to 1, and from J2 we will come back up to J is equal to 0. So the wave number that we define the expression as 2b 2j plus 3 centimeter inverse, you can just make a table of J and wave number. Okay, so filling up this table having J 0, 1, 2, 3, 4 and this wave number, simply solving this formula, putting my J value, I will get 6b, 10b, 14b, 18b and 22b. Now remember, this is something which was either added or either subtracted to my excitation wavelength. So we are going further far or we are going in a negative direction or in a positive direction, but with the same kind of difference. So for my J is equal to 0 from my excitation wavelength. So this is my excitation wavelength, that is my mu excitation. So say this is my excitation wavelength. If I add the difference of 6b, so I will get here which is at J is equal to 0. Okay, so this is my J is equal to 0. Now since this is my J is equal to 0, for J is equal to 1, from again here to J is equal to 1, I will have a difference of 10. So the difference of 10 will make here 4b, because this is 6 plus 4. Okay, so you see that this is 10, and again from excitation to J is equal to 2 we have 14b, that is again here 4b will be up to the difference between the successive anti-Stokes line here. Okay, and so these are anti-Stokes and these are Stokes. If I do the minus from the excitation incident light. Okay, so these are Stokes, these are anti-Stokes, and in the similar manner I can just simply write that the separation between the successive line is 4b. Okay, only for J is equal to 0 we have a difference from our excitation is 6b. Now the problem that we have is not that simple. So we have to note that for homonuclear diatomic molecule we are actually microwave inactive, correct, as they have no permanent dipole moment. So if you do a simple rotational or rotational spectroscopy, so they are inactive, but for rotational Raman spectra we can obtain for the we can actually obtain the rotational Raman spectra for the homonuclear diatomic molecule. And so actually when you get the rotational Raman spectra, you get value of B, and from value of B you get value of I, which is, and then from value of I you get the value of R, which is the bond length, correct? So that's what I have written, that the one can determine the bond length of these molecule also. So in the case of centrosymmetric molecules, for the centrosymmetric having the center of symmetry, for example the homonuclear molecule, for example A2, which is here AA. So we observe the effect of nuclear spin in this case. So what is effect of nuclear spin? So for example in H2, so H2 have a nuclear spin not equal to 0. It actually have a nuclear spin 1 by 2. And for O2, that is my oxygen molecule, we have a nuclear spin I equal to 0. So the energy levels with even value of J will be missing. So actually I am not going into very much detail of this. So like how the nuclear spin affect the rotational Raman spectra of these molecule. So I have attached the right link to make you understand in detail if you want. Otherwise you can just simply understand that this O2 having nuclear spin 0 will have the J value corresponding to even number, that is 0, 2 and 4. So these line will be missing in both Stokes and anti-Stoke. Okay, so the gap between the successive line will now be increased. Okay, so it will increase up will be 8. So for molecule having center of symmetry, it has been observed that they show limited number of rotational state. So what by the meaning by this line, the statement that it show limited number of rotational state, we are saying that some of the lines are corresponding to the J value are actually missing. So this was explained using nuclear spin effect, which you can understand in detail if you want to. I will attach the link. So how it happens, so there was whole understanding of the nuclear spin effect you can go through. So right now, so our problem that we have, so we have molecule O2. So we have molecule O2 and we were given that this is the Rayleigh line which was given 20491. Correct, this was the incident line. So this is my mu bar excitation. So 20491 is my mu bar excitation. So this excitation value was given to me. So this is my mu bar excitation value. So when I subtract it from the value of my first Stoke line, which was given 20479, so it was given to me that the first Stoke line is at 20479, and I just simply do the difference, and so the difference comes out to be 12. Okay, this is not B, just I am doing the difference, and it is so the difference comes out to be 12 centimeter inverse. So the unit is centimeter inverse. Now this difference must be equal to 10B. Now why I am saying 10B, because since I know that the even number lines that are Stokes and anti-Stoke will be missing. So J0, J2, J4 will be missing. So this is my mu excitation, and my J0 is missing. So my J0, which was 6B apart, is missing, and my J1 is here, which is again 4B apart from my J0, which is missing here actually. 6B. So this particular first Stoke line which was observed at J is equal to 1. Okay, so 6. So 6 plus 4B. So 10B. So as a whole it was up to 10B. So if I take the difference, it should be equal to 10B. So the 10B is equal to 12 centimeter inverse. So this is multiplication. So this B will be 1.2 centimeter inverse. So this is the part 1 that we have solved. So for the part 2 that was asked to us, that the second Stoke line, So at what position it should come, correct? So the second stroke line should come, say this is my 10b, correct? So my j1 is there, again my j2 will not be here, so my j2 will not be here, so it will be 4b, but my j3 which is here will be here, so this is j is equal to 3. So from the first stroke line that I have, it should be uh, uh, apart from up to 8b. So that's what I did, the second stroke line. Now saying stroke line will simply mean to subtract it. Okay, so so it should be at the difference of 8b. So the difference of 8b will be 8 into b. So it will be 8 into 1.2, that is 9.6 centimeter inverse. And that 8b will be subtracted from the first stroke line. Okay, if they have asked us the anti-stroke, then the subtraction will be converted to the addition. And here, since they are asking us the second stroke line, so we are doing the subtraction. So 20479 minus 9.6, giving us a value of 20469.7 centimeter inverse. So this is my second stroke line. Yes, so this is the entire solution for the linked question number 52, 53. Yes, so first we have solved for B value 1.2 centimeter inverse, and in second part we have solved for rotational stroke line, next rotational stroke line, which was 20469 centimeter inverse. And for this particular problem, you can actually go through this link, that is the nuclear spin statistic by Dr. Sayan Bakchi, Physical and Material Chemistry Division, NCL Pune. So this is the link. So if you guys have any doubt, you can ask now. Okay, it's already 6:40. So I think Gunasli is here. So I will move to that question that she have asked yesterday. So can I move forward, guys?
Yes, ma'am.
Okay. Okay, yeah. So the question that was asked was that the difference between nephlexotic series and spectrochemical series. So this is very important to understand that what are the two and where they are applied. So first of all, the spectrochemical series, we all know they are applied on both. We have the spectrochemical series for both ligand and metals. So for in the case of ligand, so ligand are actually arranged on the basis of ligand strength. So when I'm saying ligand strength in coordination chemistry, you have already gone through the ligand, the strong field, the weak field, high spin, low spin ligands. Okay, so I hope you already know. And for metal, on the basis of their oxidation number, their group, their identity, so metal can also be arranged in the basis of their oxidation number and group, etc. And we can have a spectrochemical series for metal as well. So in the case of nephlexotic series, so this series is also applied on both ligand and metals. So when I'm saying this series, so the basis of this series is on their strength of their nephroxotic effect. So one must know what is this nephroxotic effect, such that if I understand the effect, I can understand the series also, okay, for the ligand and metal as well. So simply I will explain you both. So in the first part, that is the spectrochemical series. So we all know in crystal field theory that the ligand changes the difference or brings up the difference in the energy between the d orbital of metals when it comes closer to the free ion of the metal, correct? It brings the changes in the d orbital. This the change in the energy of the d orbital, that is the delta value, that we call as the crystal field splitting parameter or energy, is very important here, because on the basis of this only, that is the crystal field splitting or parameter or energy, we divide our ligand into strong field or weak field. Also, in some cases where my metal and ligand are actually not forming any kind of complex, so for them the experiment to determine the experimental value for delta is actually difficult. So we have an empirical formula to calculate the magnitude of CFSE. So to calculate the magnitude of CFSE, this formula is given as delta naught equal to small f small g into 10 to the power 3 centimeter inverse. This is just for your some detail. This so this g and f are parameter for metal ion and ligand respectively, okay. So in 1938, the proposal of spectrochemical series was given by analyzing the result of UV visible absorption spectra of cobalt complexes. So for the cobalt complexes with different kind of ligands, some analysis was done for the UV visible spectroscopy, and then we were given with the spectrochemical series based on it, okay. So the spectrochemical series of ligand from small delta to the large value of delta, that is the ligand which are causing higher uh, energy difference in the d orbital of the metal, that is we call them as the strong field ligand, and such that we also see that these strong field ligand are also are also making the metal complex as a low spin metal complex because of the pairing of the electron that they cause. So for metal, okay, so this is the particular series you must have seen. So see, from O2 to negative, that is the weak field ligand, iodine I negative, Br negative, going up to cyanide Cn negative and up to Co, okay. So this is the spectrochemical series that you have seen till now. For metal also, if you want the spectrochemical series for metal, just arrange the metal given to you in their higher oxidation number, okay. So higher their delta value, higher they will be in the series, okay, in the right hand side of the series. So basically the higher the oxidation number, the higher the delta value of the metal also, okay, metal ion. Now coming to the nephroxotic effect. So for the nephroxotic series, we have to first understand the nephroxotic effect. So what is this effect? So this is used for the transition metal complexes, okay. So the transition metal complexes, we see this nephroxotic effect, and so in this effect there is a most important parameter, only one parameter basically is used, is the Raka parameter. So this Raka parameter, that is capital B, is actually, what is it? It is a measure of interelectronic repulsion, which occurs when a free transition metal ion forms a complex with different types of ligands, okay. So just understand it simply as I have one okay, just I have some free metal ion, okay. So this is say M plus 2, and this metal ion do have electron cloud around it. So the B, that is the Raka parameter, can also be given for this free metal ion. I'm again saying it is free metal ion, it is gaseous. Okay, so for this we have some B value. Okay, so this B value is just simply the measure of the inter-electronic repulsion for this free metal ion. Now what happens when this free metal ion comes in contact with some ligand and do complexation and make some complex. So let's say it forms some complex Ml2, correct? Now so this is the complex that it is formed. Now if I just again calculate the parameter B, the Raka parameter for this metal ion, which is now in a complex state, so this will be different from the free ion value, because it now B is just the measure of the interelectronic repulsion. So since it has the electron cloud of the metal orbital or metal, must have been distorted or has been expanded in order to form the bond with the ligand. So in that case the repulsion must have decreased, correct? So this B prime value for the metal complex will be the B prime value will be smaller. Okay, so hence this B Raka parameter get decrease in the complexation process, or in complexation of, or in Ml2. Okay, so I hope you understand this. And after this, what we do is that so yeah, the presence of this effect brings out the drawback of CFT. Also, in CFT, if you have noticed or have studied well, then you know that in CFT that only ionic bond formation is mentioned, but no covalent bond between metal and ligand is mentioned. So, but due to this nephloxetic effect, it actually shows that my metal and ligand are having some covalent character and forming some bond which is covalent in nature. Okay, so so this is again, it brings some drawback of CFT, suggesting a covalent character between metal and ligand. Okay, so if B, that is my Raka parameter, get reduced in the case, for example, metal complexation, when it formed from free ion to some complex. So this is when my B reduces, simply means that there is a less repulsion between two electron in a given W occupied metal d orbital than what it was in the free ion. Okay, the counterpart of that complex, that is for example Mn plus. So it implies that the orbital size is now larger after the complex formation. So the if my orbital, the repulsion is less, that is my orbital size is much larger, that is my, that the electron cloud must have more distorted or must have expanded. So in Greek, if you search the word nephloxotic, you will see that this is simply the expansion of some cloud expansion. So nephloxotic effect means that the orbital or the electron cloud distorted or expanded. So in that effect, what happened, that my Reka parameter of that in comparison to the free metal ion got reduced, that is the repulsion reduces. So this is simply you can understand, I hope. So you can note now the reason for electron cloud expansion effect. So electron cloud expansion effect is other name that you can give to your nephloxetic effect, because nephloxetic word just comes from Greek word that I have already told you the meaning. Number one is the metal positive charge decreases by any negative charge of the ligand. So basically there is a covalent bond formation, that is the overlap of ligand and metal orbital creating covalent bond increases the size of the orbital, and the inter-electronic repulsion will be reduced. So this reduction of B, that is interelectronic repulsion, is reduced. The reduction of B, that is the Reka parameter, from its free ion value is normally reported in the terms of nephrostotic parameter beta. Now while preparing this, I also got confused between the nephrostotic parameter beta and nephrostotic effect. So these two are you can say indirectly proportional. So when I am saying there is more nephrostotic effect, meaning that the more nephrostotic effect, meaning the electron cloud must have expanded more, and meaning that my Reka parameter for the metal complex is reduced, because it is just a measure of the electronic repulsion. So this beta prime, B prime, capital B prime, will be small in value in comparison to my free ion. So this will simply reduce my beta, which is the ratio between B prime upon B. Okay, that is B prime, that is the Reka parameter for my complex, and B for my metal that was in the free state, that in the gaseous state. So I will just say that this beta, that is the nephrostotic parameter, is actually inversely to nephrostotic effect. Okay, and now empirical formula to calculate the magnitude. Okay, so I have seen that you may be asked in your gate paper about to calculate some B prime or B, okay, so or simply beta. So or you must be given with K and H value. So this is in that case you must know this empirical formula. Other than that, I don't think so you need to know this. So empirical formula to calculate the magnitude of Reka parameter for any metal ion in complexation. So this B prime, that is my metal ion after complexation, this is B prime. Metal ion in free state, that is B, 1 minus KH, okay, and this is centimeter inverse. So this is the formula that you can use. And now the nephrostotic series of ligand. So again, this nephrostotic series is in the order of increasing an effect. When I am saying it is in the order of increasing an effect, then it must be in the order of decreasing beta parameter. That is decreasing beta parameter, meaning that beta is lowest, that is most reduction in Reka parameter of my metal complex B prime. Correct? So are you guys with me in this? You understand? Gunasli? Okay, nice. So this particular series that I have shown you here is F negative H2O ammonia. So F negative having a beta in is highest here. Okay, and my I negative having beta in lowest. Now just note down that this I negative, Cl negative and Br negative are in very different position in comparison to the spectrochemical series. So that's what I have written here as a note, that F negative, my En and my Cn negative, so these ligand occupy almost the similar position as they have occupied in the spectrochemical series. But the Cl negative, Br negative and iodine, I negative, are arranged very differently. So here the ligand with large N effect have better tendency to form covalent bond than the ligand present at the start of the series. So basically at the start of the series, that is at the left hand side, the ligand that are present in the nephrostotic series are actually showing poor covalent character or poor covalent bonding with metal. But in the case of the ligand placed at the right hand side of this series, we say that they show a higher covalent character with the metal bonding, okay, metal and ligand. So yes, so this is it. And for metal ion again, I can make a list of the metal ion following the nephrostatic effect. That is, my nephroc n effect or nephrostatic effect will be higher in the case of oxidation number, which is higher. Okay, so this is it. If you have any doubt, you can ask. So Gunasli, is it clear to you? Okay. Okay, Afrin also said yes. Okay, Shikha, is it clear?
Yes, ma'am.
Okay. So I think, uh, yeah, Afrin is new. So Afrin, can you introduce, like from what are you doing right now? MSc and from where?
Ma'am, I am pursuing my master's in chemistry, organic chemistry from DDU, Deen Dayal Upadhyay, Gorakhpur University.
Okay, okay, nice. So you have joined the this live session for the first time. So if you,
Yes, ma'am.
I will suggest you if you can go to the Gate portal. You know the Gate portal site. There you can find the video solution of till now that whatever we have posted or made. Okay.
Okay, ma'am. Thank you.
Okay. So thank you so much for joining. Thank you.
Thank you, ma'am.
Okay, so I will end this session. Yeah, thank you.